Thank you everyone for attending this talk. This joint work with Badih, Ghazi, Ravi, Kumar, Rasmus, Pagh, and Amer, Sinha. We study the distributed analytics setting where end users and the analyzer, each user I receive an input xi and then produce a message yi. These messages are then sent to the analyzer who use them to compute an estimate of some function f on the input. Here we focus our attention on the real summation problem, where each xi is assumed to be a real number between 0 and 1, and we would like to estimate their sum. We want to compute this estimate while also respecting the user's privacy. Specifically, we use the differential privacy notion of the FORC and others, which says that if we change a single user's input, the output distribution shouldn't change too much. So far, this definition is somewhat underdefined because we haven't said what is the scope of our algorithm and what is the output that we would like to be private. And choosing different scope for the algorithm will result in different models of differential privacy. On the one end, there is the central model of differential privacy, which thinks of the entire protocol as a single algorithm. And in this case, we would like to protect just the estimate that we output. This model is great in terms of accuracy because it's known that there is an epsilon DP algorithm that can achieve an error of just 1 over epsilon. For constant epsilon, this means that we can incur just constant error. However, this model also requires a lot of trust because, for example, the analyzer may even see the user's raw input. And this might not be desired in several distributed applications. And this leads to the definition of another model of differential privacy, which stands on the other end of the spectrum, called the local model. In this model, we view each user's randomizer as the algorithm, and we require that the message sent by the user to the analyzer be differentially private. This is great in terms of trust because everything leaving the user's device is already differentially private. However, it comes at a price of accuracy. Specifically, it's known that the best one can do in terms of error in this model is square root of n. This large gap between the local and central model has motivated several researchers to try to find middle ground models that may require weak trust like the local model while still attaining good accuracy of the central model. And one such model is the so-called shuffle model, which we'll be discussing in this talk. In this model, the setting is very similar to before, except that the messages, instead of being sent directly to the analyzer, is passed through the so-called shuffler, who just shuffle these messages before sending them to the analyzer. The requirement here is that these shuffled messages have to be differentially private, or equivalently, that the multiset of messages sent be differentially private. Now that we have described the different models, let us get back to our real summation problem. As stated earlier, it's known that in the central model, the best possible error one can achieve is 1 over epsilon. And in the local DP model, the best possible error is square root of n. In the shuffle DP setting, Badih et al. Show that the tight error is n to the 1/6, which is indeed between the local and central model, but it doesn't quite reach the central model yet. However, the Badih et al. Lower bound only holds when each user is allowed to send only one message. And this leads to a study of somewhat of a relaxation of the previous model, where now we allow each user to send multiple messages, and all these messages are still shuffled together and are then sent to the analyzer. In this multi-message setting, several works have shown that it is possible to achieve error that is similar to that of central DP. However, these algorithms still require a large number of messages sent per user. In this work, we show that this is not necessary. Specifically, our algorithm can achieve an error that is near central, while each user sending just 1 plus 0 or 1 message in expectation for a large range of delta. For more detail about our work, please check out our longer talk. Thank you.